Hello students, welcome to Vista's Learning. This is Shruti D. Nadiga, your chemistry tutor. We are in 11th standard chemistry and we have started with our S block elements. As we know, we have almost finished with this S block element and this is the 7th lecturing class. So when we go with the 7th lecturing class, what do you think? We have almost finished it, right? The S block elements, all the syllabus in S block elements we have covered. But why again we are teaching with the S block elements now? This is because we need to revise and go ahead with the exercise part. If we are not revising, then whatever we have been learnt will not be memorized, right? So we are getting into the S block elements exercise part. What is the first question here? Why is sodium less reactive than potassium? We know that these two are in alkali metals, right? Both are in first group itself. First we get sodium and then potassium. Why is sodium less reactive than that of potassium is a question. That means potassium is more reactive than sodium. The reason what we can understand by this is that down the group what happens? Size increases. As size increases, the sodium size is smaller than that of potassium size and the outermost electron in sodium is a bit difficult to remove than that of potassium. That means the ionization energy of potassium is less than that of sodium. So that makes the reactivity of sodium which is less than that of potassium. So why it is? It is because of ionization enthalpy. What is ionization enthalpy of potassium? It is 419 kilojoules per mole, whereas for we have sodium ionization enthalpy as 446 kilojoule per mole. So the energy required for potassium is lesser than that of sodium and hence the potassium reacts more vigorously than that of sodium. Since ionization enthalpy of potassium is less than that of sodium, potassium is more reactive than sodium. Next question. In what ways lithium shows similarity with magnesium? We have studied about the similarities between lithium and magnesium, right? So what are those similarities between lithium and magnesium? We need to mention here. So the first thing is that they can react with, see, they are asking us chemical behavior, right? So then we need to go ahead with the reactions, chemical properties of lithium and magnesium, how they are similar in properties. So when they both react with nitrogen gas, we get nitrides, right? Magnesium nitride, lithium nitride will be formed and both react with oxygen to form monoxides. We have learned that first group elements, what happens? They will be forming peroxides and superoxides, right? But lithium has the exception, it is forming the covalent bond and it forms what bond? Monoxide. So lithium and magnesium both forms lithium and magnesium both forms monoxides, right? Just a while. Next we have both elements have the tendency to form covalent compounds. What they have tendency to form covalent. What do you mean by covalent compounds? Covalent compound means the sharing of electron takes place where the ionic compound gaining or losing of electron or transfer of electron takes place. So here generally the first group elements, the lithium group elements are ionic in nature except lithium and it is having the similar property to that of magnesium. Both of them will show covalency. Next, both can form complex compounds. What do you mean by complex compounds? Means they can form coordinate compounds which forms the complex, which is not just reacting with one or two atoms or molecules. Instead, it is forming the complex with more than them. So how it will be? The complex will be like this. You can just consider lithium complex is this, just an example of that. And this is magnesium complex, which are useful in our biological terms. Next, why are potassium and cesium rather than that of lithium is used in photoelectric cells? So what does this says is that lithium, sodium, potassium, rubidium and cesium, right? So down the group size increases. So size of cesium is larger and potassium is larger than that of lithium, and for size of cesium is more larger than that of potassium. So when we know this, easily the electron can be removed from potassium and cesium than that of lithium. As we know, lithium size is very less and it has the effective nuclear charge on the outermost electron, and hence more energy required to remove the electron from lithium as the size is also lesser. So photoelectric cells, if you are doing, when you have the plate of the metal, when the light is falling on it, it needs the electrons to come out, which produces the electricity, right? So when they have to eject it out, what happens there? It requires energy. The energy, if it is having more energy to give, then it will be difficult for us to conduct this electric cell, right? So if you take potassium and cesium as the plate or the reflector, what happens? Very less amount of energy is required to remove the electron from potassium or cesium, and you can easily remove them. So you can say that potassium and cesium has much lower ionization energy or enthalpy. Energy required to remove the electron is ionization enthalpy than that of lithium. As we know, lithium is having smaller size and hence ionization enthalpy will be larger. As a result, these metals easily emit electrons on exposure to light. Which metals? Potassium and cesium. Due to this, potassium and cesium are used in photoelectric cells rather than of lithium. Next, discuss the various reactions that occur in Solvay's process. Since this is very much important, production of chemicals, we have studied about this Solvay's process, right? What does the Solvay's process have its steps? We have already studied about this. Sodium carbonate will be formed. How to form the sodium carbonate? Using ammonia, carbon dioxide, water and NaCl, right? So we'll just go ahead with this. Calcium carbonate splits into calcium oxide with carbon dioxide. Ammonia reacts with water molecule to give ammonium hydroxide, and that ammonium hydroxide, NaCl, sodium chloride, will react with carbon dioxide to give sodium bicarbonate and ammonium chloride. As we know, here ammonium chloride dissolves, whereas the sodium bicarbonate doesn't dissolve. It precipitates out, and we can take that precipitate and then heat it up again. We get sodium carbonate, carbon dioxide and water. Again, this carbon dioxide and water which is been produced can be used in the further steps where we have used here carbon dioxide and water for the same reaction. And also ammonia can be gained back using ammonium recovery. Okay, do you understand this? This is about Solvay's process. You can see sodium carbonate further reacts with water to give sodium decahydrated. This sodium is anhydrous sodium carbonate, whereas later on if you have water in that, it absorbs the water and gives you sodium carbonate decahydrated. So it is a hydrated salt which we call it as washing soda. Next, why is lithium carbonate decomposes at a lower temperature where sodium carbonate at higher temperature. That means if this lithium carbonate and sodium carbonate, if I take and heat it up, it have to undergo decomposition. For undergoing decomposition, the lithium will have lesser energy required, whereas for sodium it requires more energy. So as we know, students, here lithium and sodium, lithium forms covalent bond, sodium forms ionic bond. So ionic compounds will be more stronger than that or stable than that of covalent compounds. Hence, more energy is required for sodium carbonate, whereas for lithium carbonate, comparatively less energy. Let's see this. Lithium carbonate is covalent compound, whereas the sodium carbonate is ionic compound. So covalent compounds are less stable than that of ionic compound. A little bit of energy or heat energy if you provide for covalent compounds, they decompose. Therefore, lattice energy of sodium carbonate is higher than that of lithium carbonate. This is important now. So lattice energy means energy required to form that molecule. As I said, the ionic compounds will be very strongly placed with the each ions in the lattice, so they will be having higher lattice energy too, which makes the higher temperature to decompose that compound. Whereas for lithium carbonate, what happens? It decomposes at lower temperature, Li2CO3. Okay. Next, describe two important uses of the following compounds. So uses: caustic soda. What do you mean by caustic soda? It is nothing but sodium hydroxide, right? So where we use this sodium hydroxide? In manufacturing of soap paper and artificial silk, we use this sodium hydroxide, and also in textile industries. Even we can use this sodium hydroxide as a reagent in labs. Sodium carbonate. Where do we use this sodium carbonate? For softening the water. We can also say for bleaching the water, for laundry and cleaning purposes. And also it is used in manufacturing of glass. Next, quicklime. Where do we use this quicklime? It is used in preparation of bleaching powders. It is also used in purification of sugar and in manufacturing of cement, right? What do you mean by quicklime? CaO. You remember this? Good. Next, so we have the next question. Why is lithium fluoride almost insoluble in water, whereas lithium chloride is soluble in lithium chloride soluble not only in water but also in acetone. That means it speaks about the polarity. Like here again it comes with the covalency, and here it is a ionic compound. So what happens? Fluorine is having smaller size, where chlorine will be having larger size. When fluorine is having smaller size, that will form the covalent bond with lithium, whereas the chlorine will form the ionic bond with lithium. So the size matters here, right? So due to that size, we have this differences. So it is due to the high lattice energy of lithium fluoride as compared to that of lithium chloride. As lithium chloride is having less lattice energy and lithium fluoride is having higher lattice energy, it can easily be insoluble in water, whereas lithium chloride can be soluble in water. Not only water, even in acetone. Because why we speak about acetone? Acetone is CH3, C double bond O, CH3. Here it is also a covalent compound or molecule. It is a hydrocarbon. Okay, so even that given lithium chloride is soluble in water as well as in acetone. Why? Because it is having less lattice energy. So lithium chloride is soluble in water because its hydration energy is higher than that of its lattice energy. They can easily attract the water molecules and they can produce the solubility in water. Explain the significance of sodium, potassium, magnesium and calcium in biological fluids. So sodium, where do we use the sodium exactly? So sodium ions participate in the sodium ions participate in the transmission of nerve signals and also in flow of water through the cell membrane. We know this, right? So when the cell membrane is being maintained, here outside we will be having sodium ions, inside we will be having potassium ions. Even the letting out of the energy, we use ATP to form like coagulation between them. For blood coagulation also we use this ions. In transport of sugar and amino acids into the cell, we use the sodium ions. Where do we use this potassium ion? They are used in activating the enzymes. The enzymes will be there to activate or enhance their rate of reaction. We use this potassium for enzymes. They also participate in oxidation of glucose to produce ATP. The oxidation of glucose will take place in presence of potassium such that ATP will be produced easily. Next we have magnesium, where all enzymes utilize ATP in phosphate transfer requires magnesium as a cofactor. And also magnesium is main pigment for the absorption of light in plant, which is that pigment chlorophyll. So inside the chlorophyll we have magnesium to trap the light from sun, which is used in photosynthesis. Next we have calcium. Calcium ions are present in bones. They are very much important for us, and also in neuromuscular functions these calcium ions will be useful. What happens when these compounds, metal, react in or dipped in water? Which metal is this? Sodium metal. Sodium metal is very vigorously reacts with water, as we know. It reacts and it produces hydrogen gas, and the heat energy, that heat energy will meet the ignition temperature of hydrogen and it catches fire. So it reacts very vigorously. So sodium reacts with water to give you sodium hydroxide with evolution of hydrogen gas and also a lot of heat energy. Got it? So sodium metal is heated in free supply of air. Then we get sodium peroxide. What is this? Sodium peroxide. That means oxygen will have minus, each oxygen will have -1 as the oxidation number. So we can also write it as O2 -1. That means each oxygen will have -1 as a oxidation number. So we call sodium peroxide. When that sodium peroxide dissolves in water, we get back again the sodium hydroxide with hydrogen peroxide. When sodium peroxide is dissolved in water, we get sodium hydroxide and hydrogen peroxide. See here, sodium reacts with water to give hydrogen and sodium hydroxide. Here sodium reacts with oxygen to give sodium peroxide, where that sodium peroxide again reacts with water to give sodium hydroxide and hydrogen peroxide. Next equation, we have sodium peroxide reacts with water. So when sodium peroxide reacts with water, we get sodium hydroxide and hydrogen peroxide. Next, potassium oxide. Potassium oxide with, can you say, is it peroxide or superoxide? So K will be +1, O2 will be -1. So when we crisscross here, we get KO2. So that means O and O, both O, O2 will be having -1. That means each oxygen will have half or 1/2 as a oxidation number. So minus 1 by 2. So what is this KO2? KO2 is a superoxide. Potassium superoxide reacts with water to form potassium hydroxide with evolution of oxygen and formation of hydrogen peroxide. Sodium oxide. Is it sodium oxide? Can you see that? Sodium plus 1, oxygen minus 2. So when we crisscross, we get Na2O. So this is 1 oxygen with minus 2 charge, normal oxygen. So it will be sodium oxide. This is sodium peroxide. This is potassium superoxide. So sodium oxide reacts with carbon dioxide to form sodium carbonate. Got it? Good. Next, we need to arrange the following in the increasing order of its solubility in water. How do they soluble in water? So they have given magnesium, calcium, strontium and barium of same second group elements, and they have given the chlorides, not fluorides, bromides or iodides. They have given same chloride salts of second group elements. So how to give the increasing order of the solubility in water? So if we take barium, have larger size, right? Then we have strontium, then calcium, then magnesium. That means down the group size increases and ionization enthalpy decreases. As ionization enthalpy decreases, the lattice energy will also be less. So it can, as soon as if you add into the water, they can easily dissolve. Which can dissolve if it is having larger size. So barium, strontium, calcium and then magnesium chlorides. Why do alkali metals give characteristic flame coloration? As we know, we have electrons in the outermost shell. If you give a very less amount of we have the electron in the outermost shell. If we give the less amount of heat energy, it will excite to the higher energy level, and then after some time it will come back by emitting out the absorbed radiation, and that which is emitted out will be in visible region, and hence we get the coloration in the flame. So alkali metals, due to low ionization energy, absorbs energy from visible region to radiate complementary color. Got it? So by this we finishes our division for part of S block elements. In the next class we will go ahead with the P block elements. Students, if you have missed any of the classes, you can browse into our web application www.v-learning.in. So we Vista's Learning will be having all the videos in other languages also. You can just browse into our web application. And thanks for watching Vista's Learning.